Today I will talk about work. As you know, work in the physics equals to force time distance. And in chemistry, we talk about work for the gases. For instance, we have a piston. We have a gas particles inside this piston. And we have an P external pressure. So in order to move the piston here, we need an external pressure. If we apply a force, we can increase internal pressure or we can decrease the volume of the gas inside the piston. But how can we define the work here? So firstly, we change the piston position this much, which is for instance, a distance L. So I can define the work here as dV, force times dl. Force is actually created by the pressure, but there is a relationship between the force area. So this is the area of the piston, and this is the area of the piston, of course. The pressure, this external pressure should be equal to force over area. So the area is constant, but we can write the F. So I want to replace the F since F is not useful for me right now. I can write A times P external for the force. And I will make a rearrangement for our formula for here. And work change will be equal to force or A times P external times dl. So first we have to realize something important. Volume inside the piston inversely proportional to dl. So if we increase the L, which is here, this is our L, volume of the piston decreases. So this part decreases. So there is an inverse relationship between them. Or I can write the A times dl equals to minus dV. Since A times dl actually represents the volume. And I want to show the volume as capital V. Okay, so I want to put the things inside. So the work A times dl was defined as minus dV. P dV stays here. I want to write the minus sign at the beginning and dV. So this is the work. To get rid of from the dV or dW, we can integrate both sides. So it is the easiest thing here. If I integrate from the V final to V initial, for instance, this is the V initial and this is the V final, right? Then we can obtain work in chemistry. And it will be work will be equal to V external, V final minus V initial. So this is our work. What we should know is that if the P external equals to 0, it means that work will be 0 since this is a free expansion. This is the first important point. And the second important point is that we may not know the P. And in order to understand the P external, and if we don't know the P external, always we can use ideal gas law, which is PV equals to nRT. So P here can be written as nRT over V. Right? We know that part. For the reversible isothermal expansion, we can make some arrangements. What does it mean, isothermal? Isothermal means that delta T equals to 0. So we are moving the piston without changing the temperature, which can be done in a ice bath or water bath, whatever. So we have an ice bath here, for instance. Okay, we have ice particles, and the temperature of the piston, whatever we do, will stay same. And we want to move the piston slowly to not to make an experimental error. So delta T equals to 0. So I am talking about the reversible isothermal expansion. And simply, I don't know what is the P. So if I want to calculate work in this case, so we derive the work formula, which is P external times dV. And I can write for P nRT over V dV. There's a minus sign, of course, from V final to V initial. So nRT and V are constants. Not V, sorry. V is not constant. Of course, V is not constant. 1 over V, in integral of the 1 over V is ln V, from V final to V initial. Ln is natural logarithm, and this thing should be equal to nRT over nRT times ln V final V initial. And this is useful for the reversible isothermal expansion case.